So hi everyone, thanks for coming here. I'm Prashant, and I'm a PhD student at Dartmouth. If you go to a lot of hacker conferences, you would have heard of Sergey Bratas. I work with him, and being an academician, I present most of my work at academic conferences and not so many hacker conferences. So this is actually only my second hacker conference talk, and I generally work in like language-theoretic security, as the title says, LangSec. And I also work on fine-grained access control policies for ELF binaries, and that's my Twitter handle. First, just a bunch of acknowledgements. Someone paid for my trip, and some of the work that I'm presenting is going to appear in like a book chapter and a conference proceeding soon. And I work with a bunch of people, awesome people. So thanks to all of them. In this talk, I'm going to quickly summarize why parsers are important, and I'm going to speak about what LangSec is all about, and I'm going to talk about a library that we built, which is called Hammer, which is a parser combinator toolkit, and then I'm going to talk about how we applied our technique of LangSec to IoT protocols, application layer IoT protocols, and I'm gonna like show you some code. I'm usually worried about demagogues not being happy on this day, so I have snippets of code, and I'll also show you some tests that we wrote and how we go about testing our parsers to make sure that they're good. So first, parsers and security. So this is the story of how parsers actually, parser combinator toolkits, and how LangSec as a field actually came about being. And where I go to school, Dartmouth is a very cold and icy place. And the motto of the state is live free or die, and we just call it live, freeze, and die, because that's what happens every day. And long ago, in a galaxy far, far away, not that long ago, only around 2011, that's when my lab actually created this field of LangSec, and people like really wrote very bad code, and people still do. So parsers are traditionally the front line of any application. Like a parser is the part of the application that actually receives the input and makes sure that it's good. And parsers are dangerous. Because they can, if you have a bug in your parser, then that's like a gateway to the rest of your program. And a parser has to ensure that all your preconditions for your protocol are met. Like your protocol has a bunch of syntax. It has to verify each and every of those syntax are right and verified. And a parser is also a gateway, as I said earlier, it's a gateway to an attacker. An attacker, if they are aware of what parser bugs there are, like if an attacker fuzzes it and knows that for what inputs your program can crash, then an attacker can actually use this particular parser as an engine of computation. Most of our ideas over here stem from formal language theory, and I'll give you a brief primer to that soon. And so parser code, so what we say is that parser code should look like the grammar. So any protocol has a grammar and a formal specification, and the parser should stem and look exactly like that grammar that was written in the specification. And quite often, specifications don't have a clear-cut grammar. They have only long pages of verbose text, thousands and thousands of pages quite often. And you sort of, as parser writers, like we sort of have to go through these thousands of pages and extract the grammar out. And so as you see in this diagram, it's not super clear. I apologize for that. I didn't anticipate this. But so what you can see in this diagram is basically this, that you write a program expecting only a certain set of inputs. And any attacker, or anyone for that matter, can send your program a bunch of any input, any garbage input. So how does your program actually make sure that your program only accepts the certain set of input? Sanitization is not really enough. You need to have a foolproof parser or a bulletproof parser, if I may, that can like make sure that your program only accepts the expected set of inputs and rejects all the unexpected set of inputs. So what can really go wrong in parsing? Object boundaries in messages could overlap. Like you could have messages where the boundaries for fields in your packet format is not very clear, and you could have objects embedded in other objects. You could have two particular values that need to be equal and they don't end up being equal. You could have preconditions, and all these sort of lead to unpredictable behavior and hence lead to buffer overflows, memory corruptions, exploitations, and most of the popular attacks that you could have heard of. Now I'll actually go into some examples of some parser bugs that were really famous. One important one is the heartbleed bug, where the length fields weren't really validated, and that led to buffer over reads. And what really happened there was that they were using pointer arithmetics, and that didn't really go super well. So when I'll go into the depth a bit later anyway. So the Ethereum DAO disaster was another huge bug where they were using recursion, and it's not really that great when you actually have to run the code to know what really happens. You don't have any idea what's really happening, and you have to run it, and it just recurses, and it cost them a lot. They had to do a hard fork and stuff. So, yeah. Ruby on Rails sort of had this really interesting bug where they were using the eval call, and they just ended up basically just running the YAML input through it. And they were sanitizing the YAML input to convert it to something that they could actually read, and it did not go well. And it was a really popular Ruby on Rails bug, and it got really famous, and it was called Ruby off Rails. And these bugs actually translate to the IoT world as well. While we were actually working on this project, we were looking at CVE lists to see if these IoT protocols that we were looking at, the application layer ones, were they actually exploited? Not so much, but then they were still alarming. There were a significant number of vulnerabilities, and we were looking at one important one from IBM on the IBM Insight, where this was basically a crafted packet that could that would force the server to continuously be restarted. This brings me to what parsing and protocol anti-patterns we're talking about here. So shotgun parsers have parsing and code that is intermixed, and they are not demarcated. So your program sort of has to first validate your entire input. That's what we are preaching over here. And your shotgun parser is something where your validation and the processing logic is intermixed, and it's not demarcated very clearly. And sometimes you have programs that have languages that use input languages that are more complex than context-free or regular, like context-sensitive or even sometimes Turing complete. So in these cases, it becomes really hard to parse it because if it's Turing complete, it's not decidable, and you cannot prove equivalence if it's not regular or context-free. And parser differentials are another anti-pattern where you have two parsers, let's say a client and a server, that implement the exact same protocol. You want to make sure that the client and the server both have the exact same parser, and you can prove that they are both equivalent. If you cannot, which is what led to the Android master key bug, where the C++ and the Java implementations, one of them was using a uint, one of them was using an init, and you really can't prove equivalence over here. And the PKI certificates, where the client interprets the certificate in one way and the server interprets it another way. So those are examples of parser differentials, and that is also one of the anti-patterns that we are addressing through LangSec. So this is an anti-pattern in a C program, in C parsers, where there is a lot of parser arithmetic. There's a lot of pointer arithmetic that is used, and to step through variable length, pointer arithmetics aren't really the best idea, as we saw in the heartbleed bug as well. It doesn't really end up very well. So being an academic, I sort of am forced to put a bunch of Greek symbols. It's okay if you don't understand this. Everything that I told you before this, anti-patterns, can actually be formalized in this particular way. So we have three different operations here. So there is the interpretation equivalence, there's the interpretation uncertainty, that's the question mark, and then there's the interpretation inequivalence. So basically all this equation is saying is that the left-hand side is the predicate, and the right-hand side is a bunch of interpreters. So for example, in the second line where I have P, and I have the uncertainty interpretation. So over there, all it means is that there is a predicate, and A1 to AK actually interpret it differently, or they don't know if it's actually certain. I'll explain this with an example. So if you have a language L that is known to be decidable, then you have an oracle O and you have the designer of a protocol who basically who are uncertain that this particular language is decidable. So as I said, like this is just academic jargon. You don't have to completely understand this. To actually describe this in a better diagram, so we basically have three people involved in this particular anti-pattern analysis. So we have a designer, we have an oracle who always speaks the truth, and we have an implementer. So basically the idea is that the implementer and the designer, the implementer is basically implementing the design protocol, and the implementer and the designer both believe that the specification is decidable or the protocol is decidable, and the oracle knows that in reality it's not. So this leads to so that's why we have an inequivalence operation here. So in reality, the truth and what the designer or the implementer think are like actually incorrect or not equal, or both interpreted differently. So this brings me to what the LangSec viewpoint is. So the LangSec viewpoint is this, that we want to apply formal language theory to implement these parsers. So when we are implementing a parser, we are taking into account the formal specification or the formal grammar of the protocol, and the whole goal is to prevent the recurring programmer errors that I spoke about while motivating the problem. So it's not a guaranteed foolproof solution, but it does improve the code quality and makes it more readable, and it helps you avoid a lot of these recurring issues. So LangSec basically identifies protocol. So, okay, coming back. So, LangSec identifies a bunch of problematic syntax and features, and the way you implement a parser using LangSec, it points out when the specification of the protocol is actually ambiguous and programmers disagree in the protocol implementation or specification, and if the validity check is too hard to perform, then the protocol should probably be simplified. Like there are a few protocols that we have worked with in the SCADA power grid side where we suggested that the protocol should be simplified. For example, there's this protocol called DNP3. The specification was just too hard to get right by all programmers. So we pointed this out, and like a bunch of colleagues actually worked on fuzzing a bunch of these devices to identify these bugs. And another issue is that there's too much context needed to judge if an object is actually valid or invalid. That means that there's a protocol state machine also, like the protocol itself has a state machine. Like for example, in TCP, you send a SYN, you receive a SYN ACK, and you send an ACK. So in this particular state machine, you sort of need to know in which state you are, and if the packet that you're receiving right now is valid with respect to the state also. It's not just the syntax, but it's also the overall state machine of the protocol itself. So if your state machine of the protocol is also incredibly complex, then it makes parsing also incredibly hard, and you need a lot of context to actually judge if the packet is actually valid. And several sources of truth, that would mean that you don't have just one global syntax or one global specification. You actually need to read from a lot of other places. Most protocols, most proprietary protocols, have a bunch of documents, half of them being deprecated and so on. So it makes it really hard to build a parser for like such proprietary protocols. So for people at the back who probably can't see this, let me just explain. So this is the Chomsky hierarchy. If you have taken a formal language theory class on automata, you should probably have come across this. But just to recap, the innermost is the regular grammar. The one right outside it is deterministic context free. This is non-deterministic context free. This is context sensitive, and this is the Turing machine. So over here, what happens is that formally speaking, only if your language is deterministic, push-down automata, or context-free grammar, or regular, you can actually prove that your parsers are equivalent. So if you have two parsers that you implement, if your language does not fall within these two levels, then you cannot really prove that your parsers are equivalent. You cannot prove that two implementations of your protocol are equivalent. And at the same time, if your specification is a Turing machine, if your protocol is a Turing machine, then if your protocol needs a Turing machine to validate your input, then it's not really decidable. There's the problem of there's the halting problem. So you don't really know if it's actually decidable. So you definitely want to stay within the context sensitive boundary, but ideally speaking, if you want to have two implementations that actually are equivalent or right, and you want to have some good features you want to prove, then you should definitely have your input language in this particular area. So this is how we actually, this is the overall LangSec primitive. So it's like you have an input, you have a parser there. The parser is essentially a decider for the input language. The parser says that the input that it got was like valid or invalid. And if it's valid, it will give back a whole parse tree. If not, then it would just reject the input. And then the input gets passed on to the rest of the program that actually processes the logic. So how do we actually do this? We start with the grammar. We basically read the entire specification and extract the grammar from it. And if the protocol comes without a grammar or the specification does not have a grammar, then you still have to read the entire 2,000, 3,000 page specification and come up with a grammar. We had to do this for an incredible number of power grid protocols in the past before we got into the whole IoT space. And the parser essentially looks exactly like grammar. And another important thing to keep in mind is that you don't start any processing or you don't start any sanitization or anything with the input unless you completely verify that the input is valid. So these are some principles that LangSec follows. So your valid or expected syntax must be clear from the parser code, and your parser code should be completely distinct. Your code must read exactly like a specification. Your code must accept all the, so every syntax element in your code, like every small piece of your parser, should be incrementally testable, and it should have a good testing hygiene. And the toolkit itself, which is what I mentioned earlier called Hammer, it should discourage troublesome syntax. So we do need some sort of a toolkit that can enforce these principles that we are preaching over here. So parser combinators were initially built for Haskell, but it's a really neat tool to have or to know to use. And the tool that we built is written in C and C++, but we do have bindings for a lot of other languages. And we have a bunch of parsing backends that we use. And this particular library is freely available, and it has a very neat documentation. So I would definitely encourage you to give it a try and try validating your input using it. And the code looks exactly like grammar. I've told that a bunch of times. And in this particular example, you can see that if you have a sequence number that's exactly 4 bits long, you can actually do that. It doesn't have to have byte boundaries or 8-byte boundaries. That's not really necessary here. And you have like primitives, which are like bits, bytes, and uints, and so on. And then you also have combinators, which are like choices or many or sequences to like actually group them. And you can also, we have a pretty decent API to implement your own combinators, although I don't think it's necessary, but you could if you wanted to. This is a larger table that's describing some of the primitives that we have. So we have primitives for characters, for like text-based protocols. So you could have character ranges as well. These inputs do not essentially have to be in ASCII. They could be, you could actually have them in hex. That's also valid. And then we have different combinators for uint or int, and we also have them ranging from 8 to 64 bits. And we also have an integer range that you could specify. Then we have a sequence where you have a sequence. So like a sequence is really important, and it's really something that we have to use a lot, because when we are converting like a packet format to a specification, it's really important to have something that can actually group combinators one after the other. Then there's the many, which is essentially a clean star, which is basically this, that it will run the combinator that you provide inside it n number of times. There's no maximum number for n, because a clean star is just till infinity. And there's the optional field, which will basically check if the character A exists. If it doesn't, then it will just ignore it and move on. So let's talk about some background that's required to actually understand how we build a parser, which is understanding what application protocols we are using and why we chose them. So the important the three big application layer protocols that we chose were MQTT, XMPP, and AMQP. It's primarily because our oil and gas industry partners are using MQTT and XMPP a lot in the US, and they also want to eventually scale to AMQP because a lot of cloud providers are already offering it. The MQTT protocol is like really widely deployed, and there are some very glaring choices that have been made in the protocol. For example, the subscription to the pound sign. If you subscribe to it, you can basically get all the packets from the server. And the protocol is publish subscribe, and you cannot really figure out who the sender is without accessing the logs on the server. And TLS is not enforced by the specification, it's optional. These are some really weird choices that the protocol has made. I can understand that because it's essentially targeted towards really lightweight devices that cannot do much processing, especially not crypto. By crypto, I mean cryptography, not cryptocurrencies. The real crypto. This is how the packet format looks like. There's a header. There's a remaining length, which is the actual payload, and there's the number of bytes that are remaining after that. So this particular length field does not take into consideration what's there before that, and it can range from 1 to 4 bytes in length. And then there's the payload that follows it, and the payload is basically dependent on the length field before that. The other protocol that we looked at is XMPP, which is XML based, and the specification has been worked over decades. So it's a really robust specification. It was used for chat earlier, and that's why people think that it's really good to use. And the specification does enforce TLS, and it also has some really neat features like authentication and binding, but both are actually optional in the specification. But in our implementation, we do enforce them. And there have been a lot of security enhancements that have been suggested to XMPP and MQTT for that matter, but they don't really talk about the stuff that we are talking about here. So this is how a packet looks like. As I mentioned earlier, it's XML based. So if you notice over here, the field that follows after the username is actually the ID that is bound. So you can have the same username that's logged onto a server through multiple binding IDs, and the packets will get routed to exactly. So for example, if you're logged into the same server from your phone and from your laptop, if you send it to just the username, it will get broadcasted to everyone. But then if you want to send it only to your laptop, then you can also specify that in the binding ID. AMQP is like a protocol that is built as an improvement to MQTT, and it has a bunch of additional features. And when I was scanning Shodan, there's almost 1 million AMQP brokers that are running, but of course most of them are not implementations that are empowering IoT. It's more of a message passing protocol. So it's quite popular. It's gaining a lot of traction. I mean, it has already gained a lot of traction. And the people in the oil and gas industry think that this is really useful because in the oil and gas industry, they primarily use Ethernet cables to connect. They don't use wireless communications that much. So at least over there, they think that such a reliable bandwidth and connectivity is really useful. So over there, AMQP becomes really useful. I just wanted to show you what sort of messages exist in AMQP. So there's a connection tune, open, and so on. So this particular diagram will give you an intuition of what the protocol state machine should look like and how you can actually extract a protocol state machine. Again, this particular thing is not super clear from the specification of the AMQP protocol itself. It's something that you have to manually extract after reading through the specification. So let's look at some code. So far we've implemented it for a lot of protocols, and the ones that we are most proud of are the DNP3, C37, and our IoT implementations. So the DNP3 and C37.118 are SCADA protocols, and those implementations were written in C and C++ for various reasons. And the AMQP implementation that we worked on, like it was written in Python 2.7, and the XMPP and MQTT implementations were written in Ruby. So there are two important components that we need to actually start building these parsers. So first of all, we need to know all the protocol syntax, and we also need to know the overall protocol state machine. So for XMPP, how we went about it was that we had a protocol state machine, and for each state in the state machine, we had a parser that was running. It had a specific parser for that particular state. So once you move from state to state, you had a separate parser for it. And the XMPP implementation specifically was written in Ruby. So we used a gem to actually enable us to do the state machine work. And we used our Hammer library to actually implement the parsers itself. So this is an example of how the state machine looks. So you can specify a bunch of pre and post conditions for the transitions, and you can have a bunch of transitions that are basically events. And basically, when the transitions occur, our parsers get triggered every time. And this is how the grammar itself translates. Again, I apologize for the lack of clarity. So you can see over here that you specify the hex symbol for white spaces, double quotes, new lines, and so on. So you build ground up, and eventually when you have the entire stream, so you have a stream open tag that takes a sequence. Which is the uint8 of the type, and then you have 2 bytes for the channel, which translates to a uint16, and then you have 4 bytes for the size, which is over here. I'll get to the and right after. And then you have a sequence of the class, method, and a bunch of arguments that are optional features. And then you have an end frame that is just a CE, which is fixed as per the protocol. So this is how when you have a packet format, it translates exactly to a parser. So this whole thing would recognize the parser. Now, coming back to the AND field over here, so there's a need for us to actually read this particular size field and then make sure that the rest of the packet is actually that length. So that's why we have an AND combinator, which would actually not move the parser pointer past this particular field, but it would consume everything that is there inside. But the pointer is still over here. The pointer is still before that particular AND is executed. So that's why we have to recognize size again after that. This particular combinator would only make sure that the length is valid towards till the end, basically. So as I mentioned earlier, that this is another protocol that we are actually fairly proud of, and this was one protocol for which LangSec actually got a lot of recognition. So over here, this is the DNP3 protocol. As you can see, again, this is the byte. These are the raw bytes that you see on the wire, and you can see how these bytes actually translate exactly to code. So over here, I'm introducing another combinator called the token, which would basically take the entire string as it is. And then the length is actually validated over here in the attr bool, which would basically return a true or false. And there's a method that does the validation, which is validate CRC. And there's a validate length as well towards the end. So attr bool can basically run a method to do a bunch of validation on your program. And this particular DNP3 implementation is fully open source, and you can definitely go take a look. So how do we actually validate these parsers that we build? So one important metric that we use is the timing analysis to make sure that we meet the latency requirements of the protocol itself. And we also write a bunch of unit test case based on CVEs that we see and we also fuzz our parsers to make sure that they don't accept input that we don't that it shouldn't. Talking about performance, like we were running them on Raspberry Pis. We did eventually run them on more constrained devices, but that data is not yet available to us. So on a Raspberry Pi, we saw that it was in the order of microseconds for us for the AMQP protocol, and it was in the order of a few seconds on the constrained devices. And we also saw that the lines of code was very reasonable. So think about this particular benefit that you have of actually making sure that the packets are fully valid, and the lines of code is still like under 50. So it's not that much of a programmer effort to actually ask your programmers to implement these parsers in this particular way. And we did the same analysis for MQTT as well, where we found that the CPU time that our parsers were consuming was still in the order of microseconds, and the lines of code were much. Parser validation. And we also fuzzed, okay, now I'm louder. And we also fuzzed our implementations using AFL. And you can see that there were no crashes and there were very few hangs as well over a period of 24 hours. So this is another tool that we built, which was to generate some, I believe that most of us know how fuzzing works, but I'll still give you a primer. So fuzzing essentially takes some seed input, which is like a bunch of valid packets, and then it basically mutates those packets to generate generate test cases to actually run your code through. And even if you don't actually give it a seed, it will keep mutating from null. But your fuzzing technique will essentially work better when you have some seed given as input. And in our particular example, so in this particular tool that we built called Kegi, we were like using the context-free grammars or the parser combinators as a specification and providing that as an input to this particular fuzzing tool. And our fuzzing tool was essentially only generating all the valid set of input, and we were valid set of input based on the specification that was already given. And we essentially fed all this input to libfuzzer, and libfuzzer mutated all these seeds and ran it through the input. So working with libfuzzer was interesting for us, primarily because we had collaborators who were actually building this tool. And essentially, libfuzzer does not require a main method. It only requires a target method, which actually takes a data pointer, and it also takes the size of the input. And you basically call your method over here, and it takes these two arguments. And we essentially converted our Hammer implementations to so that we will be able to fuzz it using libfuzzer, and where you have a parser input, and then you have it takes two arguments, the same as libfuzzer itself, and it basically runs this particular check. So h_pass will actually run this particular data through this particular parser, and the size is also specified so that it doesn't overshoot the pointer. And then if the result is valid, which is like it's not null, we perform a bunch of actions. So this particular method, if the parser is written in this particular way, we can actually provide it as an input to libfuzzer itself to fuzz our implementations. And compiling with libfuzzer, this is something you can again look up on the tutorial. And you have to use Clang with libfuzzer, and you provide a bunch of sanitize arguments. And this particular last one that you see, lhammer and the pkg config, is something that that's how you provide the path to our Hammer library. And yeah, then you just run, you compile and you run, and you see a bunch of fail cases, or you see a bunch of sigvs and so on. So that brings me to some concluding remarks. So LangSec is not a way for you to like be completely sure. You cannot be completely sure. You have to fuzz your program. You have to follow good hygiene. But at the end of the day, LangSec does provide a disciplined roadmap for success. There's some really exciting work in the LangSec space that's coming up soon. There's the DARPA SafeDocs program that's coming up. And then we are also building a parser generator that's on top of. Yeah, yeah, yeah. So you do need to know the entire protocol to write the parser, but for DNP3 we have one available already. So we have an entire implementation of DNP3 and it's open source and it's available, and it also withstood like some state-of-the-art fuzzing techniques like ages. Yeah. Yes, you can. Both. We have implementations of both. And we do implement the application, not just the application layer, we also implement the data link and the IP layer of the DNP3 packets. Yes, it is black box, but we also use Aegis, which is white box. If you know about Aegis, it's a tool built by Adam Crane and Chris Sistrunk. So that particular tool is white box. So we also use that technique to make sure that our implementation was correct and good. Yeah, yeah. It's not super different, but we wanted something that would take a parser combinator input, because that's the tool that we were using. We wanted to provide our fuzzer with valid inputs that were generated from the specification that we have. So that's why we went with this approach. It's not super different, but we wanted to use this approach because we wanted to go from a parser combinator to a fuzzer. Yeah. Yeah.
So this parser, like one is your protocol implementation. You're basically advocating to move into this parser. Are we also going to that at a language level, like C level, like to integrate with the compiler itself?
I didn't really get your question. Could you repeat that?
This parser would be parsing the high-level code there. Right?
Yeah.
Before we and then do some.
Yeah.
Make it more friendly versus.
Yeah.
So currently it is at the. So if I think of a tool chain, where does the parser fit? Is it before the compiler? Is it the compiler, or is it the text I write itself? Is, I'm writing a C code.
Yeah.
Then the parser is coming in, or I'm writing in the parser format itself.
Okay, so it's actually unrelated to that. So it's like what you're saying is like a parser for a programming language itself, and what I'm advocating for is a parser for an input language. So for example, when you have a program like let's say an MQTT client that basically sends a message to the server and it receives a message back. So when the program receives a message back, you receive it on a socket, and then you basically do some processing or you do something to the input, and then you start. So you first see the input and you want to make sure that it's valid, and then you start basically extracting data out of the input, right? So by a parser for an input language, I'm advocating that the bulletproof shield that you have that sees and makes sure that the input is valid is what the parser is, and it should be extracted from the formal specification.
So the parser is a program.
Yeah.
Any of these concepts applicable for like if you have REST APIs and stuff like that?
Yeah. Yeah, it can. So the question was, can it be used with REST APIs? Yeah, of course. So the assumption here is that the REST API libraries that we use do follow good hygiene for validating the input. And that's not always true. So you could follow this particular approach to make sure that your REST API, the library that you use to provide REST APIs, actually validates the input and makes sure it's correct.
Okay, so you have like support for Python?
Yeah, we have support. We don't have it for JavaScript yet, but we do have it for Java, Python, Ruby, .NET also, and apart from C and C++ and Python.
So if I'm developing a REST API, do I need to, how do I define like, so what are the value inputs? So it has to be defined in ASN syntax or
So
what exactly I need?
So you need to.
If I don't specify everything like that, using the library will not be a problem.
Yeah. So you do not need to specify it in ASN syntax, but you need to specify in the parser combinator syntax, which is very similar to ASN syntax. So the thing is that ASN code generators in the past have had a lot of vulnerabilities themselves, right? So that's why we didn't want to go the ASN way, because ASN has been used to like extract cryptographic programs and cryptographic libraries, and they have seen a lot of vulnerabilities in the past. So we didn't want to go in the ASN one direction, and we chose our own parser combinator syntax. That's it. Thank you, everyone. This is my contact information. Do shoot out an email if you have any more questions. Thank you.